Hello, sir, it's not audible. Hello?
Yeah. So now,
Yes, sir. It's audible.
okay. Okay. Should I start from the first, like the earlier slide, or I'll continue from
Previous slide, sir, please.
previous slide?
Yes,
Yes.
sir.
Okay. So here I was telling that basically the diffusion process is what we call as a if you move or transport some of an atom A into another solid B, for example. So that is what we call as a diffusion process. So this diffusion couple is a very good example how this diffusion process occurs. Particularly in this case, we are taking example of copper and nickel. Why? Because copper and nickel they have very good solubility. So that means copper can replace a nickel atom and form an alloy. So similarly, nickel can also easily replace some of the copper atoms and form the alloy. But if you put it at a room temperature, for example, so you see a clear boundary here. So at the interface, there is no copper in nickel or no nickel in copper. That means you have 100% copper on the left hand side and then zero copper after that. And similarly, you have 100% nickel on the right hand side and then it is zero afterwards. But if you increase the temperature, so slowly what happens that you have some copper that will move into a nickel and similarly some nickel will move into copper. So this is what we call as a diffusion. So diffusion of copper into nickel, similarly diffusion of nickel into copper. So what you have is a mixture of blue and red. They are now mixing up, and similarly the concentration will also change. So you see a 100% copper on the left hand side, but again some finite concentration will be there as you go into the nickel. So the same thing will happen for nickel as well. Okay, so this kind of substitution or this kind of diffusion process is called as a vacancy diffusion. So that means what is happening here. So your nickel, let's say when nickel enters into copper, so it will replace a copper, create a copper vacancy, and that vacancy position will be occupied by a nickel. So this similarly the same will happen for copper in nickel as well. So why this happens? Because they have a similar atomic radius, very similar, very close to each other. The electronegativity difference is very small. So some of those points we already discussed. So another diffusion process that also happens is called as an interstitial diffusion. So this interstitial diffusion is again that correspond to the interstitial vacancy that you have in a solid. So this interstitial vacancy is some space that is available like a octahedral or a tetrahedral vacancy that is available in the solid, and in that case that space will be occupied by a smaller atom or a smaller ion, and this atom then can move from one interstitial site to another interstitial site. So there can be fixed interstitial sites normally in a FCC or a BCC. So this atom can move to one of those interstitial sites and will lead to a diffusion process. So another diffusion also happens that is called as a short circuit diffusion. So this may happen normally. It will happen along the defects, the other volume defect that you have. So volume defect like a grain boundary or a dislocation that you have. So 2D or 1D defect that you have, it can happen through that because those are very high energetic regions. So it will be very easy to move any foreign atom along those grain boundaries or along the dislocations. So similarly on the external surface also, because you have incomplete bonds, so atoms can also move on the surface, external surfaces as well. So these are the basically the major diffusion mechanism is through this vacancy diffusion and interstitial diffusion. But short circuit diffusion can also happen through the grain boundary and other defects that you have in the solid. So the diffusion process is basically depends on a concentration gradient. So this is what we call as a something as a driving force. Something to happen. So that means the atom has to move from one position to another position. So there has to be some kind of a driving force, or a, a there should be a process by which it should happen. So that causes your concentration gradient, because like we discussed also in the last class, like if I put some vapor, okay, so it will just spread everywhere in a vacuum or in a room, because there is a difference in the concentration gradient. Okay, so this is what this example here it shows. I have a thin metal plate, okay, and it is separating two gases, okay, so same gas, but there are different pressures. So on the left hand side, so you have a pressure PA, which is much higher than the gas that is on the right hand side, which has a pressure PP. So here you have a high pressure, means you have a high concentration, and you have a low concentration on this side. And because of this concentration gradient, so there will be a, a force that will lead to the movement of this gaseous atoms. It will penetrate through the metal plate and then come outside to the side B. Okay, so we can define how this diffusion occurs through a term called as flux. And in order to find out the flux, so we will say J is equal to this M by AT. So that means it depends on the concentration or the mass of your the gas atom. Okay, so what is the mass of that gas atom, atomic mass, divided by the area of this plate and time. So this is basically a definition of any flux when we define. So how much matter is flowing across a cross sectional area per unit time. So if I uh, say something like a flux of water, for example, through a pipe, so the same thing, I'll be using the same formula. So how much water molecules are passing through a given cross sectional area per unit time. So if everything is in a equilibrium condition, so we will call it's a steady state diffusion process. So this is the ideal situation. What it means, that you have certain number of concentration on the left side, on the A side, for example. So the pressure is fixed or pressure is constant. So that means number of atoms or number of molecules or whatever the gas molecules, so it is the same all the time, so it is not changing. So that is the equilibrium situation, and it diffuses through the metal and comes out on the other surface, and that also will hold the pressure constant on this side as well. So you have the same constant pressure on this side, same pressure on this side, although the pressure on the left hand side is higher than the pressure on the right hand side, and that causes the diffusion. And there will be no accumulation or any uh, atoms or molecules will not get confined to a region, so they will always continue to flow through this metal surface. So that is what this steady state means. And this is the steady state diffusion. The flux is given by the Fick's first law, which is proportional to the concentration gradient, so dc by dx. So since we are talking about a flow only along one direction, so we are assigning it as a x direction, so that's why we are taking it as dc by dx. And the proportionality constant that we are writing is d. Okay, so the minus sign indicates that there is always a flow from a higher concentration to a lower concentration. Okay, so that is the minus sign is used for. So this diffusion coefficient is a important parameter here, so which is normally measured in meter square per second, and this d will depend on, so we'll see later on, it will depend on temperature as well as what kind of material or atom we are talking about. So in a steady state situation, so the concentration gradient will be always given by this dc by dx, which is a constant. So the slope will be always the same. So that means on A at, so if this represents the surface A, so that will have always a concentration Ca, and on B side, so the concentration will be Cp. So this slope then will be constant. But this is like more like an ideal situation, which is not true. So more practical thing. Okay, so here the example we discussed also, like a purification of H2 gas, hydrogen gas. So what you can take here is like, you can take so normally for purification to get hydrogen gas, so how it is done, so a thin plate of palladium is taken, and on the left hand side you will have all the mixture, hydrogen, oxygen, nitrogen, so all the gases. Now the palladium has a selective diffusion, that it will only allow hydrogen to diffuse through it, so other oxygen, nitrogen will not diffuse through a palladium. So then what will happen, so on the B side, so you will get a hydrogen gases, hydrogen molecule on this side. So this is how you can purify hydrogen gas. This example is just the extension of this formula that we talked about, this J equal to minus D dc by dx. So what it tells you that if we want to compute what is the flux through a iron plate, so you have an iron plate where it is exposed to carbon. Okay, so on one side you have a lot of carbon, and on the other side you have no carbon, and it is done at a temperature of 700 degrees Celsius. Uh, and you want to find out like what is the flux. Okay, so in order to do that, you need to know what is the d, what is d, so which is given by here, and what is the concentration difference, Ca minus Cb. So Ca is given, yeah, so this is 1.2 and 0.8 kilogram per meter cube. So that is the concentration. So on one side, A has a concentration of 1.2 kilogram per meter cube, B has concentration of 0.8. So that is what you substitute. And the position, the thickness of the plate is about 5 millimeter. Okay. So this is that you introduce here, and then just do the calculation. So you'll get this much flux. So from here, you can also calculate how many carbon atoms will actually involved in this process, because you know the flux and atomic mass. If you know, so you can calculate. So as I said, most of the cases in a practical situation, they are not equilibrium cases. So what we call as a non-steady state diffusion. So this is governed by Fick's second law, which is given by this partial differential equation. So del C by del T. So this is a partial differentiation of concentration as a function of time, is equal to del by del x, again a partial differentiation of d into del C by del x. Okay, so this what we are saying, so this represents your flux. So that means the flux is changing with position, with x. So otherwise it will be zero. If flux is, so in a steady state, this j will be fixed constant. So if I take so j, the flux at any position is fixed. It is not changing with position, or also it is not changing with time. Okay, so it is the same. So that means, but this is definitely not true, because all the cases, so there will be some fluctuation in gas pressure, So somewhere some gas atoms can get accumulated or agglomerated or can be confined or absorbed by the metal plate. So the flux will definitely change over a period of time as well as over space. So this is what this equation captures that physics. So you have a change in concentration, partial derivative with respect to time is equal to, so the partial derivative of your j with position. So in some cases, what is assumed or observed that this d, the diffusion coefficient, does not really vary as a function of position. So this d has no x dependence. So that means I can take it out from this differentiation, okay, and then I can write d into del square c by del x square. So this is a kind of a good approximation, because in most of the cases diffusion coefficient will remain the same everywhere throughout the space. Now, what is the consequence as if I want to plot the concentration of like something that is diffusing across a surface as a function of distance? So earlier we see, yeah, so this is like concentration, how it changes as a function of distance, which has a constant slope. Okay, which will not change with time. But here, so this concentration is changing when space, so you don't have a constant slope, but also it will change with time as well. So if I increase the time, so the concentration, uh, so if I go to, let's say, this position, for example, I fix a position, distance, and I look at a time t1. Okay, so here at this t1 there is concentration is 0. Then over T2, so the concentration has increased, and over T3 again concentration has increased. So even like if I wait longer, maybe the concentration will increase further as well. So that means at the same place, over time, the concentration is changing. So this is the non-steady or non-equilibrium case. So if it is equilibrium case, so this would not happen. Uh, so how do we solve this equation? So this is a very important question, because by solving this, so we'll be able to know like how much. So if I am, let's say, want to introduce some concentration or some amount of a gas or any other solute, okay, or any other atom in a solid, so I have to solve this equation. So then only I can find out, okay, after certain time t and up to a certain depth x, let's say, or certain distance x, what is the concentration I get. So solving this is a what we call as a partial differential equation. Okay, so this kind of equation in mathematics is known as a partial differential equation. So there are many situations this kind of equations comes across in physics as well. So to solve this, so you need certain conditions. So these are called a initial condition and boundary conditions. Okay. So this is also what normally is used when solving equations in electromagnetism, for example. So you need some initial and boundary condition to solve, even in quantum mechanics, for example. So you need boundary conditions to solve this differential equation, so Schrodinger equation. So similarly here also we need a certain initial and boundary condition. So here I will give you an example which is most often is encountered in material science. So, so there are other possibilities as well, but I will only discuss one possibility here. So here we have taken an example of a semi-infinite slab. Okay. So these are the conditions that we have right now. So this is what we will use to solve this partial differential equation. So what we are saying, before diffusion, so before anything happens, uh, so we will, if we have any solute atoms or this substituted atoms, or that atom which we want to diffuse into the material, it has a uniform distribution or concentration C0 within your main or a parent solid. So I have taken a piece of solid here. Let's say I'll give you example that little later on. So I have taken some solid, and what I say is initially before diffusion, so the concentration of that foreign atom which I want to introduce has uniform distribution everywhere. That is C0. The and so what we want to diffuse this pink color thing what we are talking about. So this is the extra impurity or atom that we want to add into the solid. Now initially what happens, so to solve this, so we have to define a axis because we need to know what is x. Okay, so that axis is this x axis, and we say x is equal to 0 on the surface of the solid. So this is x equal to 0, and x will increase as we go further here. And what is, how do we define the time? So time, we set it to 0 just at the instant when the diffusion begins. So when diffusion starts, so at exactly that will be our time 0, t0. So you can write these conditions in a mathematical form. So all these three statements can be written in a mathematical form. So the initial condition, we said t is equal to 0. Okay, so the diffusion just has started, and the concentration of your solute within the solid is equal to C0. It is everywhere, it is the same uniform distribution. So it doesn't matter whether x is 0 or x is infinity. Okay, another thing which also this x infinity implies that we have a semi-infinite slab. So that means what we are also assuming, that these atoms will, when we are diffusing, so they will never really reach the end part of your solid. So they will be somewhere on the surface, or they will go up to certain depth, but they will definitely not enter completely into the material. So that means whatever depth you are looking at will be much higher than the total dimension of the solid. So this distance, let's say, will be much higher than these atoms which they will diffuse up to the depth. Okay, so that depth or distance up to which they will enter will be much less than the total length of your solid. So this is the initial condition. And what is the boundary condition? So when diffusion has started, what we are saying is C is equal to Cs. That means the concentration on the surface will be the same all the time. So this is our x equal to 0, which defines the surface of the solid. So on the surface, the concentration of your whatever gas or solid that you want to diffuse, so will be always constant. C is equal to Cs. And this semi-infinite slab condition, boundary condition, means you do diffusion for as long as possible. So t is greater than 0, so diffusion has started. But at x equal to infinity, so far away from the surface, so the concentration of your uh, impurity atom or gas atom will be always C0, which is the initial thing. So it is not going to change. So the C equal to C0 at t equal to 0 will always be true even when I go to x equal to infinity. Okay, so only that means the concentration, and another thing, this concentration Cs on the surface will be also fixed. So that means anything that changes in the concentration will be up to certain depth, delta x within the solid. So if you use these conditions and solve the differential equation, so you will get this solution. Okay, so Cx minus C0 by Cs minus C0 will be equal to 1 minus. This is a very special function, error function. Okay, so this kind of, so when you solve the differential equation using a boundary condition, so that means you will apply this you say, okay, at t greater than, so at x equal to 0, for example, so you write down what is the differential equation at x equal to infinity, what how the differential equation would look like. So you use those and then solve it. So you'll get this solution. And this special function is called a Gaussian error function. So this is a typical function that you get when you solve this kind of differential equation. Okay. So this error function, so what you have in the bracket is x by 2 square root of 2 square root of so 2 square root of d into t. Okay, so you have, so this is now a function of x and a function of time. Okay, so your concentration at x now varies as a function of x, so as a function of depth as well as over time. uh, so this is how the variation would look like, okay, at a particular time t, for example. Okay, so if I say cs, this is always, so I said initial condition c0, it is everywhere c0, okay, within the solid. Now the diffusion has started, so when diffusion has started, the concentration on the surface will always be the same, cs. Now within the depth, so this, there will be a non-linear, so this is how it will vary as a function. This is a error function now, Gaussian error function dependent. So this is how it will look like, the plot. So this 1 minus uh, error function as a function of x by 2 square root of dt would look like this. So if you fix t, so it will look like something like this. If you change t, so this will appear something, it will be like, in the beginning it will be like this, then as you increase t, so it will be, then go further and further. So we will use this particular problem to solve a very classic problem in material science. So a classic problem here is, so you take a still, okay, so still structure. What you want to, so still is normally you have iron and you substitute about, let's say, about 2%, so less than 5% typically. So you substitute with carbon. Okay, so not substitute, but carbon goes as an interstitial substitution. So there are several interstitial sites within iron, and carbon will occupy that, and that normally this iron and carbon what we call as steel. So there may be some other elements are added also, chromium or uh, chromium is added, nickel is added. Okay, so various other uh, atoms are also added, but very minute fraction. But majority it is iron and substituted. So some interstitial substitution of carbon. Now, what has been observed that if you put an extra bit of carbon, so you make the structure harder. So that means you improve the mechanical strength. So that means normally what is observed that the corrosion starts from the surface. So that is where you want to make it more, you want to make it more mechanically stable, or you want to improve the mechanical properties on the surface. And that is what why you want that you need more carbon on the surface. So if you add more carbon on the surface, so it becomes harder, so difficult to corrode. So this is what the problem is. So you have a alloy of iron and carbon, which has a uniform concentration of 0.25 weight percent. So this is the initial concentration you have, C0, 0.25 weight percent. So now on the, so you want to increase some amount of carbon on the surface only. So you, it should not enter completely into the structure, but only on the surface. And so what you have done is to do that, so you have increased the concentration on the surface to 1.2 weight percent of carbon. So this is the cs, the surface, what is the concentration of carbon on the surface, 1.2 weight percent. Now what you want, like at a depth, certain depth of x, okay, certain depth is 0.5 millimeter, you want that the concentration of carbon should be 0.8 weight percent. So this is what you want. And this is on the surface you have maintained. So this is you have introduced carbon which has 1.28% of carbon. So some gases form, for example, and within the structure you have 0.25 weight percent carbon. So you want to find out how long you have to do this process at a temperature of 950 degrees Celsius. Okay, so you have introduced carbon on the surface which is 1.28% at 950 degrees Celsius. Now you want to find out like how long I should do it so that I get a concentration of 0.8 weight percent at a depth of zero point 0.5 millimeter from the surface. So in order to do that, we need to know what is the diffusion coefficient at this temperature, 950 degrees Celsius. So this is 1.6 into 10 to the minus 11 meters square per second. So this is again, you will get a data from various databases. People have done this kind of measurement, diffusion coefficient measurement. So we'll see how this can be measured actually. Okay, so now we know all the values C0, Cs, Cx. So these are all initial conditions, and Cx is now we know what is Cx as well. So we know Cx, we know C naught, C0, Cs, we know what is X, we know what is T. So we want to find out T. So if you substitute all this, what we have just wrote down, so you'll get, so which is equal to 1 minus error function in brackets. So all these things will be there. So only thing now we want to find out T. So the left hand side, if you solve, becomes 0.4210, which is equal to error function as a function of this factor. Now the question is, how do we solve? How do we find what is the value of what is in the bracket? Okay, so this is some function of z, for example. So this is z. So how do we know this value? What should be z? So this is done again from a table. So there is also mathematical table also available where what is the value of error function for a given z is known. So if I say z is 0.35, so the error function is has a value of 0.3794. So this is again comes from mathematics. Okay. So if I say z is 0.40, the value is 0.4284. But our value is 0.4210, something in between. This is what we want to find, and what is the corresponding z. So that is what we want to find. So in order to do that, so you have to do a sum of interpolation. If you do this interpolation, so again, so you know, so z minus, this is again from mathematics, we are just simply using the mathematics. So z minus 0.35 and 0.4 minus 0.35, so is equal to this error function. So again, a linear kind of interpolation we are doing, so linear interpolation. So you'll get z is equal to 0.392. So this bracket that we want to calculate, so is equal to 0.392. So that is what we are writing. So 62.5 second, square root of second divided by square root of t is equal to 0.392. Then you can solve for t, and what you will get is 7.1 hour. So that means I have to keep the process, do this carbonization process for 7 hours so that I get a concentration of 0.8 weight percent at a depth of 0.5 millimeter. So these kind of exercises helps us in designing experiment, particularly like doing this diffusion, how long we have to do this diffusion process. Okay, so what are the factors that affect the diffusion? So what is the species or atom that is involved in the diffusion? That definitely first of thing will always affect this diffusion process. So diffusion process means we are saying, so whether the diffusion will be a faster or slower, that is what we are always interested in. Okay. uh, so here an example will uh, help in understanding that. So we talked about this diffusion of carbon in iron. So normally the carbon diffusion is much faster in iron compared to iron in iron, okay, or for that matter chromium in iron. Why? Because carbon goes to an interstitial diffusion site. So anything that goes to an interstitial, so always is a small atom, so it can easily go from one interstitial site to another interstitial site. But if I want to substitute iron with chromium or even iron with another more concentration of iron, so that will be slower because iron atomic radius is larger. So it will take longer or the diffusion process will be slow if I take a self diffusion process or let's say an atom or a substitutional diffusion. Okay. So we saw earlier two types of diffusion. So substitutional diffusion will be longer compared to interstitial diffusion. So similarly, the diffusion process also depends on temperature. So how? So the diffusion will be faster if the value of D is higher. Okay, so diffusion coefficient is high, and diffusion coefficient has this kind of dependence. So this is again Arrhenius like dependence. So you have d is equal to d0. It is a temperature independent exponential term, some constant. So this d depends on the activation energy for diffusion, which is normally measured as joule. So how much energy you give per mole or electron volt, how much energy you give per atom. So that depends on that defines the diffusion coefficient. So R is the gas constant, which is again a constant, and T is the temperature in Kelvin. So that means if I increase the activation energy, so the diffusion coefficient will be small because it's negative. Now similarly, if I increase temperature, so the diffusion coefficient will be high, so it will be faster. So if I want to increase the diffusion coefficient, so I have to lower the activation energy and I have to increase the temperature. So this is this expression normally you can write in a logarithmic form. So you if you take log base to the 10 on both sides, so you'll get this equation. Okay. So now what you can do is you can now plot. So this equation looks something like a y equal to mx plus b. So this is your mx and this is your b, the constant. So your x is 1 over t. Okay, so this is your x. So you plot log d versus 1 over t. Okay, so then you will estimate what is a activation energy for a particular atom. Okay, so what will be the activation energy for carbon in iron, for example, and also that you will get from the slope, and from the intercept you will get this log d0 value and then d0. So this is how people normally do this kind of experiment, and then you plot this diffusion coefficient. This is in logarithmic scale, as you can see here, and then you plot reciprocal of temperature. So 1 over t. So it will be just a straight line. Okay, so y equal to mx plus b. So then you see in which so carbon will diffuse. So always you can see as you so reciprocal is increasing means temperature is decreasing. So temperature is decreasing as you go along the x-axis means diffusion coefficient decreases. So that is what always will happen. And also from here you can see the intercept will be much higher. For example, aluminium in aluminium. So that means the diffusion or the activation process will be activation energy is much higher. Okay. But if you look at carbon, for example, so the activation energy will be low. So here is a question. So rank magnitude of diffusion coefficients from greatest to least. So we want to find out. I have these four situations. So nitrogen is diffused in iron at 700, chromium in iron at 700, nitrogen in iron at 900, and chromium in iron at 900 degrees Celsius. So you can rank like which will have the where the d value or the coefficient, diffusion coefficient will be higher, and where it will be lower as a rank. So if you want, you just look at this and write down your answers, and maybe you can find it out later. So I will not write down the, I will not give you the solution. So you need to find out yourself. I'll give you, if you want to write down this question. Okay. So another interesting aspect of diffusion, it corresponds to diffusion in semiconductors. Okay, because when we talk about semiconductor, this is a very important class of materials, and you want to make semiconductors, like several kind of diffusion is done on a semiconductor material. So you can start with a diffusion. For example, you want to introduce, I earlier talked about a boron or a phosphorus to make it p type or n type, or arsenic to make it n type. So different atoms you want to diffuse into a silicon to make it N or P type. So similarly, you also put contacts, okay, metal contacts on a semiconductor, so that you can then connect and read electrically whatever you operate it electrically. So you also want to put some contacts on that. So in each case, you want to deposit some of those metals or any other element into semiconductor, and you want to do it at certain temperature so that they diffuse into the material. So this diffusion process in semiconductor, particularly metal diffusion, is done in two-step process. Okay. So one is called a pre-deposition step, and another is called a drive-in step. Okay. So what is a pre-deposition step? So pre-deposition step is done at a relatively low temperature, so 900 to 1000 degrees Celsius. So this is where you introduce all these whatever element that you want to introduce into the semiconductor material. So this is like the earlier situation that we talked about, the non-steady state of introducing carbon into semiconductor, sorry, carbon into iron. So here, so you want to introduce any atom, say a boron, phosphorus, or maybe some metal you want to introduce into the semiconductor. So that means you start with a gas phase. So normally, as I said, gas of boron or phosphorus or some other metal, like the gas form of that, and that you maintain a constant concentration on the surface. Okay, and that means you can use this semi-infinite slab equation that we derived, those conditions. So you can use and calculate what will be the concentration of a particular atom up to a certain depth in the material. So you just simply use like what we did earlier in the example. So you use the same formula. Only thing, you now need to know what is the diffusion coefficient of that material in silicon. For example, if I take silicon as a substrate, or silicon as a semiconductor material. So this is what we use for initial introduction of the dopants. Okay, so this is the first step you do. But then what you do is, in the next step, you call it as a drive-in step. So that means you want to now distribute this whatever. So initially you have now have certain dopants, but now you want to redistribute it. Okay, so you want to readjust so that these atoms then move somewhere, and like you want to change the concentration now without increasing the concentration itself on the surface. So that means the surface concentration, so you will not introduce any gaseous phase or anything. So this is what we call as a solid phase diffusion. You do it at a higher temperature, so 1200 degrees Celsius. Why? Because gaseous atoms will be easily, can easily penetrate. Okay, so they can diffuse through the solid. But once you have the solid atom kind of thing, so they will be slower, so you need more energy to move them. So you need a little bit higher temperature. And also what you do is you do it in an oxygen atmosphere. Why you do that? So if you introduce oxygen atmosphere, so what you do is normally for silicon, so you oxidize the silicon surface. Okay, so silicon dioxide will form. And why it is necessary? Because when you are doing this diffusion process, the second step, drive in, because of the temperature, so diffusion is a random process. Okay, so it is not like it will happen in only one direction. So since now there is the concentration is, there is not a big difference in the concentration gradient, so now the diffusing atoms can go uh, further into the semiconductor, but they can also come out of the semiconductor as well to the surface. That is also possible, because if you remember, this is, there will be a short circuit kind of diffusion can happen, because surface atoms have low bond energy. So it can happen that some of those diffusing elements or atoms can also come to the surface. This also could happen. So to prevent that, so you want to oxidize, because the silicon dioxide is a very good, you could say it's a blocking layer kind of thing. So it blocks the diffusion process. So what it will do, it will force all these solid atoms to go much deeper into the semiconductor. So in that case, the concentration, the equation is governed by this equation. So again, this comes from again some initial condition and boundary condition you have to use. So you'll get this exponential kind of function. So this is again some constant here. Not constant, there is a temperature dependence of course here, and the concentration will decrease exponentially over a distance x and over a time t. So this is what we call as a redistribution and deeper diffusion of the dopants. Okay, so these are very crucial two important steps that are used in semiconductor diffusion process. So if you look at this figure here, so this is like the first pre-deposition step. So where we have a constant surface concentration, and then we get a uniform concentration in the depth. Now we want to redistribute. So again, you increase the temperature. So this is after drive-in. So you get this blue curve. So you get a redistribution of the atom. So that means now you have a deeper distribution. So that means initially at this depth, so the concentration was this much, and now you have, after driving, you have increased the concentration in this depth. So basically what you do is in the drive-in phase, so you start with this T1. So as you increase the time, so you will go to the equilibrium, the deeper diffusion process. Okay. So now depending on what is the depth you want up to which the atom should go, so you will decide whether I should do the diffusion process for time t2 or t3 or more. So you'll decide that, because that will decide what will be the depth up to which you will have this dopant atoms. So the depth will change accordingly. So यहाँ पे depth, so in this case the dopants are up to this depth. So here the depth has increased, and here again the depth has, so it is going deeper and deeper into the semiconductor. So this distance into the silicon is sometimes called as a junction. So because here you have some uniform concentration, and here you have more of that, so what you have created is a kind of a junction. So it could be a p, so initially you could have more n, and then you introduce the p type dopants and then make a junction. So that's why this, knowing this distance is important, because you know at what depth my junction has been formed. And this is again calculated from this expression which you get after solving this equation. Okay, so if you solve this equation, so you will get an expression for the junction depth. So this is quite important for semiconductor industries to find out what is the depth where the junction is, so that they can then design their devices in the future. Okay, so I'll stop here, and before we move into another topic, if you have any question from this section, diffusion part. No question? Okay. So we'll move to the another topic here. So where we will discuss about the mechanical properties of metals. Okay. So in the beginning, I told you that one thing what we are interested is looking at a structure, and then what are the properties. Okay, so the structure affects the properties. So here we want to understand like what we mean by this mechanical properties of metal. So there will be certain parameters that you are interested in or you should know, so that you can tell that okay, my material has a better mechanical property than any other material. So here I am showing you a very nice picture. This is of Howrah Bridge, which is in Kolkata. Kolkata. Okay, so this is the famous Howrah Bridge. So this is known as one of the oldest suspension bridge. So you have basically two columns here, and the entire bridge is supported by these columns and these zigzag patterns here, which are basically steel structures. Okay, and to it is able to carry many vehicles, many weights. Okay, so over like last century, okay, it is still there. So that is the beauty of these mechanical structures. Okay, so there are many several such bridges and mechanical structures where you use this kind of features, okay, materials which have a specific mechanical properties. So you that's what you need to know, that what mechanical properties I should look at and how I can find out some of those mechanical properties so that I can use for some of these structural applications. So you need materials with high strength and high stiffness and mechanical properties. So this is a picture or an apparatus how you can which you can use to measure something the mechanical properties, and under a particular kind of force what we call as a tensile force. So you'll see what this means. So this is the schematic of that. So that means you want to test. So you have, let's say, synthesized your material, and then you put some load on it. So load is like a weight you add. So you are applying some force, and then you show or you see like how long or how much force I can apply so that it will not break or it will not fracture. So this is what you are interested in. So some of those terms you need to know. So which again comes from the elastic properties of material. So one is we define stress. So stress is the force per unit area. Okay, so this is stress. Then there is this is called as engineering stress, because the way you are measuring. So what you are measuring is not the true or actual stress, but the engineering. So you design, make the specimen in a special form, and that is why we call as engineering material, engineered material. So this is the engineering stress, engineering strain. So which is the change in the length delta L by the original length, and most likely what we want that they should follow the elastic properties, that is Hooke's law. So the stress is directly proportional to strain. Okay, so this will be the modulus of elasticity. So sigma is equal to E into epsilon. So this that means what you want they should behave. So this is the kind of graph you generate when you do this kind of experiment. So you are applying some stress, okay, and you will measure the strain, the change, and you plot it, and you generate this kind of plot. So we'll see what this plot means shortly. So look at in detail this plot. Okay, so when you want to measure the mechanical properties, so you can apply various kinds of load or various kinds of deformation you can do. So the load, why we are applying, we want to deform the solid and see how much force we can apply until it is completely breaks apart. So how much it can withstand before it completely fractures. So there is something called a tensile load. So that means by adding this load, so I'll increase the length. Okay, so I'm extending it. This is the tensile load. There is a compressive load. Okay, so that means I'm compressed as the name suggests. So I'm compressing it. So by applying the load, I'm compressing it. So in the tensile, I'm elongating it. So by applying a tension or a force, I'm elongating it. So there is also a shear load. So that means if I apply a force like on the surface, so what I'm doing is I am tilting it about an angle theta. So a shear load. So there is also a torsion load, so which will now twist the sample. So there are different way how you can introduce this kind of loads, but most of the mechanical properties that we are interested in you can understand just from this tensile and compressive load. So you don't have to, unless you are talking about very complicated motor design where the torsion or shear they can experience. For example, you are making gear or gear for a vehicle or for like electrical motor. So in those cases, probably you have to look at these other loads. But let's say for structural application, so this tensile and compressive load testing is good enough. So what we want, as I said, it should follow the elastic behavior. Okay, so that means the deformation is elastic. So which we call as a which follows the Hooke's law. So that means it is linear behavior. So everything is linear. So that means I'm applying a load. So if I'm applying a stress, as the stress increases, strain increases. So you go like this. Now if I remove the load, I decrease the load, so it should follow the same path. Okay, so this is what do we mean by linear behavior and elastic deformation process. And the slope, this sigma by epsilon, which is equal to the capital E, will give me the modulus of elasticity. Okay, so in some cases, in some materials, so this will be for most of the metals, it will be the case if your stress is reasonable, you are applying. But in some materials, you don't have at all a linear behavior. Okay, so for example, most of the steel that you make, so they really don't follow a linear behavior at all. So they are already non-linear in nature. So in that case, how do you define the modulus and the stress relation? So normally what you do is either you take a slope, so tangent. Okay, so let's say you say what is the modulus of elasticity about a certain region in this curve. So you take a tangent, so delta sigma by delta epsilon. So that will be get a tangent modulus. Or sometimes what you do is you calculate what is the secant modulus. So how do you calculate the secant modulus? So you take one point will be the origin, another point will be, let's say, this point. Okay, so that corresponds to stress sigma 1. So you calculate what is the delta sigma by delta epsilon. So of course here it will be sigma 1 by epsilon. So that will be your secant modulus. That is between origin and sigma 1. So this is some kind of way you can understand the elastic process in this non-linear materials. Okay, so these are the, so if it is elastic, that is quite clear. So you get a slope, it will be everywhere same. But in this case, the slope will be different depending on how much stress you are applying, but it is still in a elastic region. And why this happens, this deformation happens? So this modulus of elasticity, so when you look at the atomic scale, so it depends on how strong is the bond is. Okay, so you have, so we talked about structure. So the structure is due to the bond between two atoms. Now if the bond is stronger, so the elastic modulus will be, so it will be difficult to break that bond when you are applying some kind of stress. It will be difficult to break those bonds. So it will be more elastic in that sense. So that means this slope will be the elastic modulus dF by dr. So this is again correspond to your slope to the force curve. So this force as a function of interatomic separation. So if it is weakly bonded, so the elastic modulus slope will be small. The slope it will be steep slope if the if it has a strong bond. So that means if it is a strongly bonded material, so the elastic modulus will be high. So this is how it is related to the atomic structure here. Okay, so but normally when people do experiment, so they will not really stop in the linear region. So they will further increase the stress. Why? Why you want to do that? Because you want to actually investigate what is the limit up to which, what is the maximum limit up to which you can apply stress on a particular specimen or a particular material. Because if you want to use it for a certain application, you should tell, okay, so this is the maximum stress or maximum weight it can withstand. So if I increase the weight more than this, so then it will break. So that is why you need to investigate or measure even beyond this linear region. So what is that region is called? That is called as a plastic region or plastic deformation. So one we studied, if you have the linear part, we call it an elastic deformation. Okay, so if you go beyond, again it is not a linear one, non-linear. So we call it a plastic deformation. So this is the plastic behavior of the material. So in this plastic region, what we call it is a permanent change. So we have a permanent change of the structure. What it means? So in elastic process, so if I am extending it, there is an elongation due to the tensile force. So if I remove that force, so it will come back to the same shape and same form. But now if I go into the plastic deformation region, and so I am applying a tensile force where I am taking into a plastic deformation region. So in that case, when I'm removing the load, so your material may not come back to its original shape and how it was originally is. The original length, original shape, it will not come back to that. So this is, so therefore the plastic deformation is a permanent change and elastic is a non-permanent change. Now there is like this transition from elastic to plastic is very difficult to predict. Okay, so you really cannot say exactly like a particular point or a particular stress where a value where it will do the transition. So because it's a gradual change. So there, in this case, a point P is defined, which is called as a proportional limit. Okay, and you say it is kind of going from a linear to a non-linear behavior. So that will be like the onset of your plastic deformation process. Okay, so then there are some other terms also we need to define here. So one another very interesting feature. So if you do the measurement actually, so you will see it goes to like a linear. It is still linear, and then there will be a jump. So this is how a typical behavior looks like when you do the measurement. So there will be then a decrease in stress. Okay, so the strain is increasing, but stress is decreasing, and it almost like fluctuates a little bit, almost like a constant, and then again it increases. Okay, so this is a typical experimental curve. So what you define something called as a upper yield point and a lower yield point. Okay, so particularly this lower yield point is quite a feature which appears in most of the metals when you apply this tensile load or a tensile force, and that's why this point is used. So you just draw a line. So you see and like a constant behavior in the curve, and you draw a line, and the value, the stress value that you get, what you call as a yielding or yield strength. Okay, this is the name that is used, yield strength. Okay, so the sigma y is called the yield strength. Okay, so if I further increase, so what will happen? So now if I still keep on increasing the stress, so I already entered into the plastic deformation stage. That means I'm not, it is a permanent change. I'm not going to get back to my original size and shape. But if I increase, so what will happen? So in a plastic deformation process, so what happens, you will, so this is some a typical curve that is that you observe. Uh, so this point M, so M, so already everything is in the plastic deformation region. So this point M, this is the maximum of this curve. So you have a maximum of stress corresponding to the strain. So this maximum point M is called the tensile stress or tensile strength. So what you call as a tensile strength. So this point will define the tensile strength of the material. And then if you further increase, so what happens? Eventually it will break. So there will be a fracture. So this point F will be called as a fracture point. So that means, so it will break and you will not be able to measure anything. Okay. So this is a typical metal, how the stress strain curve looks like when you do this experiment. So you apply a load, a tensile load, so that means you are elongating it. So if you are in a elastic region, so when you remove, so it will come back. So this is, let's say this is what your material is, and this is where the load, like you are stretching it. Okay, so uh, by extending these 2 points, okay, so you are stretching this material. Now if it is in the linear, so if you now remove this, it will come back to its position. But once it enters into the plastic region, so now there is a elongation, but then it will not come back. So it may recover some of the features, okay, but it will not come back to its original position at all. And then as you keep on increasing, so what happens, something like a neck formation happens. Okay, and once this neck formation happens, so then it will break at this. So this is a typical behavior of a metal under deformation. So another interesting property of metal, when we talk about mechanical properties, so one is called ductility. So ductility means, so if I am applying a tensile force, so I can actually make it more like a wire. Okay. So if I take, for example, copper, so I can make a wire out of it, or a gold, I can make a wire out of it. Okay. So this is the ductility of the material. But other metals, they are the other opposite of that is brittle. So that means they will really break easily, so without forming this wire kind of thing. So from this stress strain curve, you can immediately say whether your material is ductile or brittle. Okay, so if it is a brittle material, so you can measure up to certain stress, and then there will be a fracture. So you will never reach this tensile strength. You'll never know what is the tensile strength, because you will not get this complete curve, so it will fracture before that. So this is, that will show you the brittleness of your material. So if it is ductile, so you'll be able to measure this curve. Okay, and you can measure also quantify this ductility. So percentage elongation, so this percentage elongation will be given by the final length before fracture. So this is before fracture, what is the final length, minus the original length divided by L0. So if you multiply, so you can percentage ductility, you can also calculate. So yeah, so here is a table which shows you some of the mechanical properties of different metals and metal alloys. So as you can see, aluminium has a very low yield strength, 35. So 35 megapascal. So if I apply 35 megapascal pressure, so this is measured in pressure, so 35 megapascal. So then it goes from a elastic to a plastic deformation. But if I look at, for example, steel, okay, titanium, so I have they can withstand 180 megapascal, 450 megapascal, for example, before they go from a elastic to plastic deformation case. So similarly, the tensile strength will of course also will vary. So aluminium has about 90 megapascal, steel has 380 megapascal, titanium 520. So you can really deform it. Of course, you are going into the plastic deformation, but still they will not fracture even if I apply this much pressure. Okay. So that's why most of the structures, the bridge structure, you use a steel. So you don't make it from aluminium or copper. So iron can be used, but steel is a better preferred material. So it is low cost and also very high tensile strength. If you look at ductility, for example, so aluminium has a relatively high ductility. Copper, yes, good. Brass, that is copper and zinc alloy, 70 and 30, also very high. But if you look at steel, the ductility is very low. So that means what you can already kind of notice a correlation here, that if the tensile strength is high, the ductility is low. Okay. So this is a kind of a correlation. Normally, you will also observe in most of the metal and metal alloys. So that's why if you want to make a wire that is used electrical wires, for example, you use copper or brass, which are very ductile. Okay, so this is just a summary of this different property when we talk about mechanical properties of a material. So you need to know this modulus of elasticity E, the yield strength, tensile strength, ductility. So then also there are people also measure something about modulus of resilience, toughness, hardness. So this hardness is also very important parameter. So we'll not discuss the mechanical engineers. They always look at this values. Hardness. What is the hardness of a material, for example? So that means it will be a number. So normally it is given by a number. So there are specific tests already described by some international committee, which tells how to do the test, how you prepare the sample. So I can just give you example. So you take a material and you do a indentation. So that means you come up with another, like a diamond, for example, which is the hardest material, and you press it with certain load. So you apply 10 kg, 30 kg, 100 kg, 200 kg, and then you see how much depth it has made into your material. So that depth will correspond to certain number, which you then translate into hardness. But most of the time, if you do this stress strain measurement, so you'll be able to calculate all these parameters and you can figure out the mechanical properties of your material. So one example, I'll just talk about this plastic deformation of polycrystalline materials. This is interesting. When you make a aluminium can, for example, or aluminium or tin or some other can, for example, so you take like this kind of initial structure, and then what you are doing, you are applying some tensile force to form this kind of structure. So using a mold, so you apply this kind of a tensile force. So now you are elongating it, and eventually you get the can that you are. So of course it is not a finished product. So again you have to do some polishing and something other processes. But even at least you get a form of a can which you can use for storing some liquid or any other thing. So, how this is related to microscopic properties, like how we can understand this change if you look at the microscopic properties. So, microscopic things means we are looking at the grain size, grain distribution. Okay, so that is what we are interested in. So, can we see any changes in that grain of, let's say, in the first stage and the final stage? Is there any change? Yes. So this is what how it looks like. So this is the initial case. So you this grain you can actually, these are quite big grains, so typically of a millimeter order, so which you can observe with the optical microscope. So you see most of the grains are like you could say equi-axis. So that means they have like a distribution is quite uniform on when you started initially. But as you do the apply the tensile force, so what you see, these grains are getting more and more oriented, so elongated in a particular direction. And in which direction? In the direction in which you are applying the tensile force. So the grains are now readjusting. So that means there is definitely a movement of atoms, readjustment of atoms, alignment of atoms, grain boundaries. So as you are applying a tensile force, and this is quite interesting because again, what people then do, so you keep on applying this tensile force and see at what point it breaks, and how the microstructure looks like, how the grain distribution looks like. So you can then predict or understand what is the underlying microscopic origin of this fracture behavior. Okay, so this is a very interesting area that people do perform in material science. Okay, so what you clearly see is a change in the equiaxial distribution grain to a very elongated and oriented distribution of grains due to the application of this tensile stress in this particular case. Again, this is a polycrystalline material. That is what you also have to remember, because in polycrystalline material, this process, the deformation is very complex, because you have many grains which can uh, get affected differently, because they have all different orientation, crystal orientation within them. Another just a point which I want to just discuss here without going into the detail. This grain, since we are talking about grain, so this grain size, so not only the orientation, how that get affected, the microstructure, the size itself can also affect the mechanical strength. For example, you take so this represents two grains separated by a grain boundary. Okay, and as you're applying a tensile force, for example, so what you will do is introduce some kind of defect or dislocation at the grain boundary, because they have all different orientation. So the atomic orientation, the plane HKL, the orientation is different. And here, for example, let's say in one of the grain you have some dislocation. So this represents a dislocation. So now this dislocation will move, and it will move towards the grain boundary. And if there is no grain boundary, so this dislocation will keep on going into the other part of the grain, okay, everywhere, and this will reduce the mechanical strength of the material, because once this dislocation moves, so it could meet some other defect or other dislocation. There will be annihilation process and so on, that will affect the mechanical properties or mechanical strength of the material. So normally what happens, because the grain boundary is a high energetic region, so it will just will not allow the dislocation to move further into any where in the crystal. So what then people realized that if I want to increase the yield strength, so that means if I want to so yield strength will be higher means it is the structurality is better. So if I want to increase the yield strength, so I should take grains with smaller sizes. So this is a very interesting equation. So which relates your yield strength to the grain size. So D is your grain size. So sigma naught and ky are some constants. Depends on the material. Now, so this is a d to the power minus half, so 1 by d dependent. So that means if I increase d, so sigma y will decrease. So similarly, if I decrease d, so reduce the grain size, so sigma y will increase. So that means if I take decrease the grain size means what we call that as a fine grain. So if I take fine grains, so they will have higher yield strength compared to a coarse grain. Okay, so these are some of the terms that is used in mechanical language when we talk about mechanical properties. So coarse grained materials have low yield strength compared to a fine grain. Why? Because if I have fine grain, so I have smaller grain and more number of grain boundaries. So the grain boundaries will just will not allow any dislocation or any other defect to move further in the crystal. So all everything will be kind of stored at the grain boundary, and that's how you can improve or increase the mechanical strength of the material. So this is also people do. So what they do, they change the grain size. So how you change the grain size? So there are several ways. You can do some heat treatment process, you can do some etching, you can do some so there are other processes by which you can change the grain size. Okay, so during the fabrication process you opt a special way of synthesis to control the grain size, and you can then control the mechanical properties of the material. Okay, any question from this? So the next topic that I am going to discuss is about what we call as a phase diagram. So this phase diagram is also a very important aspect in material science. So phase diagram we know from physics point of view, like we have a pressure and temperature phase diagram. So which represents or which tells us how uh, we can convert, like at what pressure and temperature we can go from a solid phase to liquid phase and liquid phase to vapor phase. So in this case we have water. So let's say we start with solid, and then we can go to water depending on what is the temperature and pressure. So we can melt it and we can boil it and we get vapor. So this is a typical phase diagram that we are familiar with in physics. So this represents a pressure and temperature phase diagram. So we can identify basically what are the, so this is what we mean by a thermodynamic phase. So thermodynamically, so either it will be in a liquid phase or a solid phase or a vapor phase. So to further use these phase diagram concept in material science, so we need to know explore a little bit more few other terms and few other technical points. So in context of materials, why phase diagrams are important? Because they can predict, so they can predict the microstructure of an alloy. So microstructure means we just see how the grain and grain distribution is. And why this is important? Because those will tell us what are the mechanical properties of the materials. So microstructure is important because they can tell us what will be the mechanical properties of the material. So whether it is a fine grain, coarse grain, there is a big grain size distribution. All this will tell us how the mechanical properties will be. So, and phase diagram help us in predicting the microstructure. So we'll give one example and we'll discuss further later on. Okay. Before going into the discussing this phase diagram, so few terms also we need to know when we discuss about phase diagram. So one term which comes up quite frequently is a component. Okay. So component means these are two distinct materials that form the alloy. Okay, so a component will be if I take a copper and nickel alloy. So copper is one component, nickel is another component. So if I say, let's say, uh, a sugar in water. Okay, so sugar is one component and water is one component. So when I'm dissolving, let's say, sugar in water, for example. So similarly, when I'm talking about, let's say, iron and carbon. So component, you have iron and carbon. Then another term what is used is called as a system. So a system have the same component like iron carbon, but it forms a series of different alloys. Okay, so different phases. So this is what. So let's say system will be in case of this water, ice, and vapor. So system is we talk about, let's say, a solid system or a liquid system or a vapor system. So one particular phase we are identifying that we are calling as a system. Then another term which frequently comes up is a solid solution. The solid solution also we have discussed, which means that one atom is kind of diffusing into another material, and it occupies as a vacancy substitution or as a interstitial substitution. So either it occupies the vacancy that is created, or it will create a vacancy and occupy that, or it will go to an interstitial position. So this is a solid solution. Just like a solution you have of sugar or let's say your salt in water. So if we talk about solid solution, we should also know about solubility. So solubility is defined. So we are giving example here, which is well known. So sugar in water. So when I'm adding sugar to water, so up to a certain concentration of sugar, so I'll get that sugar will get dissolved into water. So I'll get a clear solution. So until that, so I'll say it is 100% soluble. But if I increase the sugar content more than given for a particular whatever the water can uh, dissolve, so then the sugar will not dissolve at all. So it will just remain as a sugar, as a solid sugar or powder sugar without getting dissolved in water. So this again gives a very interesting phase diagram here. So what we have now, another kind of phase diagram. So what we are plotting in the x-axis is a composition and y-axis is temperature. So if I say I am at 20 degrees Celsius, so now, and I am increasing the composition of sugar. So sugar composition here is 0, 20, 40, 60, 80 and 100. So since we have two system, okay, so sugar system and water system. So what we are having, so agar sugar if it is 0, so water will be 100% automatically, because you have two component here. Sorry, not two system but two component. So we have a sugar, one component is sugar, the other component is water. So we have two components. So if one component is 0, the other component will be automatically 100. So similarly, sugar here 20, water will be 80. Now, about 60 something, so 60, let's say 60 point something, sugar, the weight percent of 60 weight percent of sugar in water, so up to, or let's say, no, if I look at 20 degrees Celsius, okay, so I go along this line. So if I go up to a number like 65, let's say 65 weight percent, so up to that, so sugar will completely dissolve in water. But if I now go to 65, more than 65, so what we have, we have a liquid solution. So that means I have uh, the sugar in the sugar that is dissolved in water. Also, this extra sugar will remain; it will not dissolve anymore. So even if I increase further, so that will remain as a solid sugar. Okay, so what I have created is two distinct phases here. Okay, so a liquid solution which has water plus sugar dissolved in it, and a solid sugar. So this will vary as a function of temperature. So that means if I am going to 80 degrees Celsius now, so I can dissolve, so about 75 weight percent of sugar will dissolve. So I can increase the amount of sugar in the water solution, in the liquid solution. So this line that separates this, so earlier I have total sugar solution, what you call as a liquid solution or a syrup, the sugar syrup. Okay, so there is no residual sugar in my water. But this line, this is called as a phase boundary, which separates now two phases. So one is where there is a complete sugar solution is formed. So complete sugar completely dissolves in water, and the other part where I have the syrup plus the solid sugar which is not dissolving into this. So I have two phases here, so separated by a phase boundary. So I have one phase here, this sugar plus water, one phase. But here I have two phases. One is sugar plus water solution plus the solid sugar. So this is sorry, another kind of phase diagram. So which we will now look at more detail, particularly in the context of our material science. So here again comes two types of definitions here. So I told that we have something, a phase here. So we have a liquid solution phase, so which consists of water plus dissolved sugar. So that is one phase. So here we have also the same phase plus another phase which is a solid sugar. So this solid sugar phase is a different phase compared to the solution. Okay, so they are together, but they are two different phases. And a phase, what I mean by phase, it is a homogeneous part of the system. So here I have one system, so which can have one phase, two phases. So a system with a uniform physical and chemical characteristic. So that means if I take a syrup, so it will have the same physical and chemical characteristic anywhere here. Okay, so this is what I'm calling as a phase. And sometimes we will have a system with more than one phase. So this, we have more than one phase, so what we will call it as a mixture or a heterogeneous system. So you have either more phases, so this is a homogeneous phase or one phase, so this will be a heterogeneous phase. Okay, so another very interesting also fact which we also need to know, something called as a phase equilibrium. Okay, so whenever we look at a phase diagram, so we want to what we look at the equilibrium phase diagram. So equilibrium here means it is a thermodynamic equilibrium. Okay, so thermodynamic equilibrium means, so we talk about the system or the phase which is in a equilibrium, means it has a minimum free energy. So this is normally designated a thermodynamic parameter, that is either Gibbs free energy or Helmholtz free energy. So that free energy should be minimum. So minimum means it should not change in time. So that is what a equilibrium means. And this free energy is a function of the internal energies that are there, entropy and temperature. Okay, so this is what you already know. So mostly it will be dependent on the internal energies and the entropy. But most of the practical cases, you don't have a equilibrium phase, but what you have is a metastable phase. Okay, so this is most of the practical cases when we get an alloy, so it is not in a equilibrium phase but a metastable phase or a non-equilibrium phase. What it means, that the phase that you create has not achieved a thermodynamic equilibrium. So it is not in a minimum free energy state, but it is still a stable, a metastable stage. But it is what normally you will see most of the alloys will be in metastable phase, but they really don't change much with time. Okay. So if I make, let's say, for example, steel I will make it is in a metastable phase. Okay. So iron and carbon, but it is not like that. It has not achieved its minimum energy. There is a tendency. So always there will be a tendency to go towards the minimum energy, but the process is very, very slow. Okay. It, it's so slow that it may take forever. So it may not happen in even like during our entire life, even in the life of that material itself. Okay, so it can happen. So the process, because reaching equilibrium is very slow process. So that's why in most of the practical cases what we have is a metastable phase. Now, why we are interested in knowing different phases? As I said, these different phases will have different microstructure. So once we know the microstructure, so we can, or let's say what are the phases, and we know how it is related to the microstructure, then we can predict also the mechanical property just by knowing what is the phase. Okay, so that's why this phase diagram is important to understand and learn. So the first thing, which simplest we already discussed, this is called as a unary phase diagram. So which is basically a function of temperature and pressure. So we have temperature on the x-axis, pressure on the x-axis. So what you have is, so this separates your solid. So this line A to 0 separates your solid and vapor. So this B and 0, this line B0 or BO separates solid and liquid. So that means if I want to melt ice, so I will move across this phase boundary. So this red ones you will call as a phase boundary. So I'll move across this line so that I can go from a solid to a liquid. So similarly, if I want to go from liquid to vapor, so I have to cross this boundary OC. Okay. So if I am at atmospheric pressure, 1 atmospheric pressure. Okay. So at atmospheric pressure, so I'll start from here. So at 0 degree, so I have, this is 0 degree represents 0 degree Celsius. So that means solid ice will melt into liquid water. Now, if I reach 100 degrees Celsius, so now the liquid will evaporate and become steams. That is what we know. So this is at 1 atmospheric pressure. This is what is going to happen. But if I increase the pressure, now the solid will go to liquid, or the ice will melt at a relatively lower temperature. And similarly, if I can extend, so the temperature at which the liquid or water will become steam will also increase. Okay, so it will be more than 120 degrees Celsius. So that is why when you are using a pressure cooker, so you are increasing the pressure. So that means you are increasing the boiling point of your water. So that means automatically, so the everything boils at a higher temperature. All your vegetable, everything, so boils at a higher temperature. So similarly, if I decrease, what may happen that I can go from ice to vapor instead of, so that will not really cross, it will never become water. So ice will directly evaporate into vapor, the steam. So if I decrease the pressure, and of course, this will happen at certain temperature. So this phase boundary represents the equilibrium part. So if I look at this point, so I will have the solid and the liquid phase at equilibrium. So only if I just cross, I'll either get full solid. If I go to left, if I go to right, I'll completely get water. But here I will have an equal mixture of a solid and liquid water. So similarly, this also represents a equilibrium point. And this O, this point represents something called as a triple point. So where your water, ice, and vapor will coexist together. So this point is very difficult to achieve, but people have seen this kind of point, and only if you change a little bit from this position, so immediately one phase will completely disappear, and probably the other two phases will be there. So this kind of unary phase diagram also exists for all the metals. So you look at a metal, you melt it, then you vaporize it. So you'll get this kind of solid, liquid, and different phase and phase transition, pressure, temperature for all these different metals. But what we are interested in is a binary phase diagram. So in binary phase diagram, what you have a function of temperature and composition. So we earlier saw this sugar and water. So here we have now two compositions. So two compositions, two components, copper and nickel. Okay, so this will the example will help us in understanding this binary phase diagram. Uh, so we want to make an alloy of copper nickel. Okay, so copper nickel again, why we are choosing, because the solid solution, they are very easy to make. So they both have FCC structure. The atomic radii are similar. Electronegativities, the difference is small, so they can easily dissolve in each other. The vacancy substitution will happen. So we have a copper and nickel. So again, we are talking about the nickel. So here we are writing composition weight percent of nickel in the x-axis. So what it means? So the nickel weight percent is increasing 0, 20, 40, and here it is 100. So similarly, that means the copper here will be 100, copper here will be 80, and here copper will be 0. Okay, this is automatically understood. So what this phase diagram, what we call as a isomorphous copper nickel phase diagram. Okay. So because they have the same structure, crystal structure, so they have FCC structure. So now let's look at this uh, phase diagram and understand what it is. So what you see here, so let's say if I am 100% copper, so copper melts at 1085 degrees Celsius. So this is the melting point of copper. So that means if I go along this axis, so at this point copper will become liquid. Now, if I look at this point, this is nickel 100%, so which melts at 1455 degrees Celsius. So if I go above, nickel will be liquid. Now, in this region, so I have mixture of copper and nickel. So in this case, here, if I go to this point here, for example, so I have nickel 40%, copper 60%. So similarly, if I go here, I have copper, nickel 60% and copper 40%. So this is what you can see from here. So, but here everything is in liquid. So both are in liquid. So nice, they can mix. So there is no problem there. So now when I cool down, so now I'm decreasing the temperature. Okay, so here this is, let's say, 1400 degrees Celsius. So both are in liquid phase. So now I'm cooling down. So it crosses this line, this red line, which we call as a liquidus line. So what happens below this line? So your copper nickel, there will be formation of some solid copper nickel alloy. Okay, so if let's say I go below this temperature, so I'll have nickel solid. So similarly, in this case, if I go below this, so I will have some solid phase, what we call as a alpha. Okay, so in phase diagram, in this kind of phase diagram, so this Greek letters are normally used for the solid phase. So alpha, beta, gamma, delta will be used for a solid phase, and liquid will represented by L. So we have both now. We have solid as well as liquid. And then if I go further, decrease the temperature further, so at this point, so the liquid will not be anymore. So everything will be in alpha phase, which is the FCC copper nickel alloy. Okay. So this line is called as a liquidus line. So which separates now the liquid phase to a two-phase system, a solid plus liquid. So similarly, there will be another line. Okay, so which separates the solid, the alpha phase, and the two phase, alpha, the solid plus liquid. Okay, so this is what we call as a solidus line. So these terms are important and you need to remember. So now how do we, what we can get or extract from this phase diagram? So one thing what we are interested in to find the composition. Okay, so composition of the alloy at any point in this phase diagram. Can we find it out? So let's say if I go to point A, so what is the composition? So composition quite easy to see. Of course, you have to find out what is the temperature you are talking about. So let's say we say this point A, so which is given by this 1100 degrees Celsius. And what is the composition there? So it is 68% nickel and 48% copper. So that is what you can find out. Now, if I go to point B, so what is the composition? So this is very tricky. So it is not, you cannot just say that the composition, so you just drop a line from here and look at the x-axis and say this is the composition. Why? Because you have both solid and liquid. So you have to use a something else. So what you do is you use a tie line. So you have to construct a tie line. So also with example, so in this two phase, so anywhere in a phase diagram you have more than one phase, so you have to come up with a tie line corresponding to the temperature. So and then you have to look at the intersection of the tie line at the phase boundaries and note that down, and then draw this perpendicular line at those and then look at the phase composition. Okay, so we'll look at this example. So we have point B, so this is a zoomed in version. So I draw a tie line here. So this is along the temperature axis. So parallel to the x-axis, so along the temperature line, I have to draw a line. So this is a tie line. Now this tie line intersects the liquidus line here. Okay, so then I drop a perpendicular line here, and whatever composition I have now here, so I'll call that is the composition of my liquid phase. So my liquid phase has both copper and nickel. So how much copper it has or how much nickel it has? It has nickel of about 32.5%. Okay, so this is the point. And then correspondingly, how much copper it will have? So copper will be 67.5. So 100 minus 32.5 or 32.5, whatever it comes here. So similarly, I'll draw another line and I'll look at the solidus part and again drop a perpendicular line. And what is the, this is a solid composition of the solid. So here the nickel will be about 40, again 42 or 43% weight percent, and the rest 100 minus the nickel part will be copper. Okay, so it is not, so the composition of the alpha and liquid phase is not this. This is the equilibrium concentration C0. So this is the composition of alpha plus liquid together for this two system. But if you want to know what is the composition of liquid, so you have to draw a perpendicular like tie line first, then look at these points. Okay. The next question, what is the phase amount in a two-phase system? I have two phase, alpha and liquid. So how much I have alpha and how much is liquid? How do I know that? So then again, there is a process. So again, so this is called as a lever rule you use. So again, you have to draw a tie line. So I'll to show you the example again. So again, you draw the tie line. So you look at this length of this line. So this length from this point to point B, which we call as R, and this length S. This is what you want to measure. And then you substitute that, you will get the weight percentage of liquid. So how much weight percent or weight fraction of liquid is there in the two-phase system? So this is S divided by R plus S. Now if you substitute this R, and R is equal to C0 minus CL, and S is equal to C alpha minus C0. Okay, so this is what you substitute, you'll get this. So similarly, this will be the amount of alpha phase in that two-phase system. Again, this is quite simple to get that. So it will be 100 minus this, because you have two phases. So this WL plus W alpha will be equal to 100. So if you do in this case point B, so you will get 0.68. So weight fraction of your liquid is 68%, and weight fraction of your alpha, the solid phase, is 32%. So both, if you add up, will be 100%. So one can also convert this mass fraction or a weight fraction to volume fraction. So if you know the densities, so if you know the corresponding densities of alpha two phase, for example, so alpha and liquid or alpha and beta, so you can calculate the corresponding volume fractions as well. So you can find out. So one interesting feature, as I said, so how the microstructure changes as we go across this baseline. So this we will discuss more detail in the next class. If you have any question, you can ask. I'll discuss about this. Yes, any question? So this phase diagram, to understand, to know the nomenclature, to know these terminology, and to know that, so that you can find out what are the different phases, what are the composition in different phases, what are the weight fraction or amount of phases. So these things can be confusing, so you need to read it and understand these things, uh, and solve some of these problems, and then you will understand what it means, how one can use this phase diagram to find out the composition of different alloy and so on. Okay. Okay, so if no questions, I'll stop here and we'll see you tomorrow. Thank you.